So we need to have a serious discussion. Yeah, the discussion here is this next reaction. This next reaction is called oxymercuration reduction. But I can actually throw in another reaction with this as well, depending on what we use. And that one also has a name, and that is called alkoxy. You can probably imagine what the al stands for. Alkoxymercuration reduction. Okay. What in the world? That's probably the question that you're asking yourself. What in the world is he getting ready to talk about? Just the name alone will scare people off. But folks, I'm here to tell you that this is simple. This is easy. Easy. We already know how to do these reactions. This is just another type of set of reagents that we can use to our advantage in order to get what we want to make. That's it. That's the only difference. Oxymercuration reduction and alkoxymercuration reduction is just a fancy way as an alternative to make an alcohol. That's it, folks. That's all that we do with these. We already know how to make an alcohol, don't we? We've done it already. We've done it already. We can make an alcohol by basically taking water and adding acid. This was the first route that we've learned. Take a double bond, break the double bond, H goes on to one, OH goes on the other. We call it a day, we go on. And this is another way of ending up with very similar products. Just another way to add on an OH group. That's it. The difference, though, is that this one, there are no carbocation shifts. Now I see why we have options, because there could be a way that the molecule will rearrange itself in option number 1. Maybe I don't want the OH group to rearrange. Maybe I want it to go in the spot that I want it to go in. And the molecule is going to take that carbocation and it's going to shift it to secondary or primary, or to secondary or tertiary if it can. And that is where the OH group is going to go. Maybe I don't want that. I don't want the rearrangement to take place. Well, good news for you. If you don't want the rearrangement to take place, we have option number 2. And option number 2, you can choose, and that's oxymercuration reduction or alkoxymercuration reduction. Now, let's talk about what is needed for this reaction to go forward. Number 1, an oxymercuration. The alkene, that double bonded molecule that we've been focused on this entire lecture series, is going to be treated with mercuric acetate. And we're going to take that mercuric acetate, which is almost like a white crystalline powder. I can weigh that out, measure it, whatever. It smells a little sour. It smells like a mixture of metallic as well as vinegar. As you can tell, vinegar is acetic acid, and we see acetate into the name, so that shouldn't be surprising. So I can weigh this stuff out on a balance, and then I'm going to have to dissolve that stuff. Well, what kind of solvent do I put this in? I put this into something called THF. All right, so THF, it's very important that you know what that abbreviation means. And this is called tetrahydrofuran. That is THF. I'll show you that structure a little bit later, but THF, tetrahydrofuran, this is going to be the solvent that we need to dissolve the mercuric acetate. All right, so step number 1, let's talk about this. Number 1, as a student or as an employee for a lab, I get you to go into a lab and I say, take this acid, take this water, go do a reaction with it. I feel pretty good about that. All right, you can't really mess that up too much. And if you do mess that up, it's not going to be a disaster. I mean, it's water with a little bit of acid as a catalyst. And often for you, it's a couple of milliliters. All right, so if you do spill it, if you mess it up, whatever the case is, it's not a disaster. Oxymercurations, folks, we're using mercury. Mercury made the Mad Hatter go mad. I mean, that's why that happened. All of the mercury compound that was used in the hat making process. Yes, thank you, Alice in Wonderland. We now know a little bit of chemistry was involved. It probably also made me go crazy too, as you can tell from these videos. But mercuric acetate is nasty. Not only is it nasty to use, but it's nasty to dispose of. Once you use it, what do you do with it? You're going to have some stuff left over. You can't just dump it down the drain. Can you imagine? Can you imagine if we were dumping mercury down the drain and somebody found out about it? No. So this is the drawback with this set of reactions. The drawback is the mercury compounds are very hazardous. I don't want you exposed to them. I don't want the environment exposed to them. But you got to outweigh your options here. Do you do this and prevent rearrangement, or do you do the acid and water and high heat, or maybe at least heat, not high heat, but heat, to get that reaction to go forward? Number two, after this first part goes forward, after that reaction completes, we then need to introduce another reagent, and that reagent is called sodium borohydride. All right, so sodium borohydride is Na for sodium, boro is boron, and hydride is H4. So NaBH4, that's sodium borohydride there. So with these two sets of reagents, we're going to kind of sum up in a way what's happening here before we look at these reactions. In the first step, what happens in the mechanism is that the mercury acetate, the Hg, and acetate we abbreviate in organic with an AC, and there's an O there because it's CH3COO, so there is an O there. There's two of them to make this a balanced charge because, again, it's ionic. Mercury typically carries with it a +2, and acetate typically carries a -1. So we need two of those to balance. This is added to the double bond. Very similar to the halogenation step. You know, that halogen came on, a cyclic intermediate was formed, that ion was grabbed onto both carbons and so forth, and that prevented rearrangement as well. Okay, the same kind of thing happens here. This mercury acetate goes on, the mercury grabs onto both carbons, it grabs onto each one of them, it makes up its mind on what he wants to do, and this helps prevent rearrangement from taking place. When this happens, something's got to leave, right? If this mercury acetate group comes on to the double bond and grabs both carbons, it's got to make room for that. So something has to leave. And what leaves here is one of the acetate groups. Remember, we have two. So one of those groups end up leaving and goes away. Bye-bye. See you later. Well, Markovnikov's rule will follow. Markovnikov's rule will basically say H plays with other H's. And in this case, there's no difference. This is our electrophile, so we regard this as our hydrogen. Hydrogen plays with other H's, so this mercury compound will also play with other H's. All right, what's next is that in this mix, we are going to end up adding some type of water. So mercuric acetate and THF is first. And then in the reaction, you're going to see it. In the reaction, they're typically going to bring in water, maybe some other options for us as well, but water's probably going to be one of them. And this water, the purpose of it is what it always does. It will provide an OH group. And this OH group is added to the other carbon, which is a carbocation, or it will turn into a momentarily carbocation when that cyclic structure breaks. So keep in mind the later stages of the halogenation mechanism. Bromine went on, bromine grabbed a hold of two carbons at one time, and then that OH group or that other bromine group or that chlorine group came in and said, it's okay, bromine, you can let go. Let go, Jack. Let go. You ever see the movie Titanic? That's what's happening here. So it tells bromine, let go, let go, let go, and it does. Well, in this case, it's mercury. Mercury lets go. And then that other piece, and in this case it's OH, will go on to that carbon. This is how we form the alcohol group. Again, it's due to the water source. Well, when this begins to happen, remember that acetate was left off, right? This acetate went away. Ding-ding-ding. And this acetate group can go on to make some other byproducts. I mean, that's okay, not a big deal, whatever. It can make some byproducts, and we're not really going to be paying attention to those right now. It's not really important to the overall scheme of the reaction. But I will say that the acetate group that was kicked off, it attacks the water that we took into the system. And it rips off one of these hydrogens. And this is what will free up the OH that was needed for that reaction to take place. Now, step number 3, you got to keep in mind, mercury is still attached. Okay, we are not ending up with a mercury compound. Not in the very end of this. That mercury's got to go. Got to go. You got to figure out how to kick it out of the house. You know, mercury's very toxic. When that mercury moved in with you, talk about a disaster. It ate all your food. It used up all your water, your electric. I mean, those utility bills went skyrocketed. It brought its friends over all the time. They had drunken parties. I mean, you know, you might thought that you were in a frat or sorority house. And that's not what you want. Not in the home that you're paying for, right? So mercury has got to go. Mercury's got to figure out on what it wants to do. It's too toxic to stay here. I don't want it around. It's nice to hang out with a little bit, but after that, it is over. It's over. Got to go. So we got to get that off of there. And the question is how? How do we remove it? Well, that's the purpose of step 4, which is our sodium borohydride. The sodium borohydride will take this mercury bond, this Hg bond, and it will replace this mercury with hydrogen. And that hydrogen source, you can see where that's coming from. It's right there. That's the purpose of the sodium borohydride. Now, any reaction, and I'm going to throw out some terminology here. Any reaction that will look at this carbon to hydrogen bond, and increases the number of carbon to hydrogen bonds is called a reduction reaction. In organic chemistry, that's what those are called. So we call this oxymercuration reduction. Almost like 2 parts, didn't we? Oxymercuration, you now know where that's coming from. We are taking this organic alkene, we're breaking the double bond, we're adding mercury onto that compound in the very beginning, and we're allowing an OH group, typically from water, to go on in the next step. There's your oxymercuration part. The reduction part comes from the sodium borohydride. It's going to look at the mercury bond to the carbon, and it's going to go, gotta go, you're out. And that mercury leaves, and it gets replaced with a hydrogen, and that hydrogen's coming from sodium borohydride. Well, that increases the number of C to H bonds, and inorganic, that is by definition a reduction reaction. So now you know where the name comes from. Oxymercuration reduction. General template, let's look at this. I know this sounds horrible, like it will be bad, but it's not. I promise. Trust me. Here's an alkene. I just wrote an R group here. It can be anything that it wants to be. I'm just focused on the double bond, and that's it. We're going to draw a big, big long arrow. A lot of stuff that we got to write here. This is a two-step reaction. Step number 1, we know that we're going to bring in mercury, Hg, and then OAC, there's my mercury acetate. And then we also know we're going to have to bring in some THF, and I'm also going to write down water up here as well. So there we go. There's step number 1. Step number 2, we know it's NaBH4. There's a lot of stuff there. It looks like it's going to be a hard reaction, and it's not. It's not. Whatever. Let's take a look and see what goes on here. All right, so R, CH, double bond, CH2. Folks, this is how easy it is. Guess what? Double bond breaks. Who would have thought? And then two sides of attachment open up. There you go. Well, mercury goes on to the carbon with the most hydrogens. I'm temporarily going to write mercury here, Hg. And then the water will provide the OH group, and that water will go there. There's the other spot. And then in step number 2, that sodium borohydride comes in and says, hey, mercury, you got to go. You're toxic. Nobody loves you. Nobody wants you. You got to hit the road. Go on now and don't come back. And then it replaces that with a hydrogen. Folks, there you go. It's just another way to use an alcohol. That's really it. Or not to use an alcohol, but to make one. This would have been the same product that I would have ended up with in this example as if I used water and acid, but not every single time. And the reason is because no rearrangement happens here. Very important that you scribble those down often. No rearrangements. That way you can kind of keep a cheat sheet in a way of reactions that allow rearrangement and those that do not. And it's always that list that I want to pay attention to. The ones that have the exceptions. And now we've seen 2 of these. Our halogenation reactions, no rearrangements can happen. And then our oxymercuration reduction reactions, no rearrangements can happen there either. So this is how we predict the product, the major products from the oxymercuration reductions. Okay. Now, just like before, I can change this to a CH3, and then that will allow me to go in and just erase that so it can clean it up a little bit, and there we go. All right, so there's our product. A lot of people like mechanisms, so if you like mechanisms, here you go. I mean, look at this to your heart's content. I'm not going to ask you to ever replicate this mechanism. There's a few that I do like for you to know. But there's also a few that I think are just so outrageous and so time-consuming and really just defeats the purpose of why we're here. This is one of them. I don't really want you to go through this one and rehash it and regurgitate it because, folks, if you can do the Br2Cl2 one, then you can do this one as well. All right? It's really the same mechanism. If you look at it, here's the mercury with the acetates that's coming in. That mercury comes near this double bond, and it does something very similar that Br2 or Cl2 does, right? That mercury grabs onto both, just like I said before, a cyclic compound kind of temporarily forms here, and one of these acetate groups go off. It goes away, and we're left with one. Then water, because we've wrote water onto that arrow, that will come into the picture and says, all right, mercury, I'm here. You can make up your mind and do what you need to do. I'm here to take the other one, though, that you've grabbed onto. So that mercury behaves like an electrophile does because that's what it is, and it goes to the side with the most H's. So that's what you see kind of pop off over here to the right-hand side. And now here is the water molecule that was added on. Well, that oxygen now says, I've got too much to handle. I can't do this anymore. I've made a mistake. I have too many bonds. I'm spreading my time too thin. So another water molecule is present. We have tons of them. Remember, we have tons of them. And that water molecule will come in and say, I got your back. I'll take this hydrogen off and I'll generate some acid. So we have acidic conditions at this point. And then this will free up those electrons so that way you can take them. And that will neutralize that OH group out. So water removes a proton to generate an acid. And then we're left off with this OH group that is very happy at this point. So that's the first step of the reaction, step number 1. Now, step number 2, we wrote below the arrow, and that was the addition of the sodium borohydride. And here's the addition of sodium borohydride. Notice they don't even do curvy arrows. The reason, and they actually state this in the text, is that we just don't fully understand the mechanism at this point. Yes, that's correct. We don't understand mechanism sometimes. You know, we have a good idea of what happens. We can kind of make a decision on what goes on, but we don't really have proof. We can't track it. All the signs lead to us to believe that this is the way that it happens, but at this point, we still don't have the concrete proof that it is exactly the way that it happens, if that makes sense. All right, so what we see is a starting product that was here. This was from our last part of that reaction that we talked about before. The sodium borohydride is then added to that molecule. We know that this piece goes off, pop, off it goes, and we know that one of these hydrogens will go on to that spot. So this is a CH2, and now it turns into a CH3. But notice there's no curvy arrow mechanisms or anything, all right? Now, the other piece that we also talked about was alkoxy, and I do want to mention something about that because really they go hand in hand. There's no big major differences between the two, and the alkoxies kind of give us a different type of product. So how does this work? So alkoxymercuration reduction. Well, as you can imagine, we still have mercury. It probably is still going to be maybe acetate here. We'll see. We'll find out. That's what the other one used. Reduction part, we probably still would use sodium borohydride or something like that, right? So how much different is this? Okay, well, mercuration reduction and alkoxymercuration reduction are very similar. In alkoxymercuration, though, we have a different mercury compound. All right, and this mercury compound is not mercuric acetate, but it's mercuric trifluoroacetate. So this is HgO2 CCF3 parentheses 2. This is the compound that's going to be used instead of mercuric acetate. A little bit more complicated, but look, folks, we've got fluorine here. Fluorine, very electronegative. Okay, we need a little bit more of a punch in order for this to go forward. And then instead of water with these, we add on typically alcohols. That's where the difference is going to be coming from, because we're adding alkoxies here. Not just oxymercuration, but alkoxymercuration, which means that we need a oxy and a alkyl group, and that alkyl group would be something like CH3 or CH3CH2 or an isopropyl group, something, and that is coming from alcohols and not water. That's the major difference that we have here. I mean, no big deal other than this. That's it. We still use sodium borohydride in step number 2. It still does what it needs to do as far as the reduction part goes. But folks, this is the only difference. So in one version, we have oxymercuration. All right, and that's water. This water will split, and this is the oxy part of the oxymercuration. Well, in this case, alkoxymercuration is very similar. This will split, just like water did. H and then the remaining part. H and then the remaining part. But this is the alkoxy piece, the alkyl group and the oxy group, and that is alkoxy. So that's why we name it the way that we do. But in order for this to go forward, we need a little bit better of a punch in order for this reaction to start. And that is due to the fluorine that is very high in electronegative value, and there's 3 of them in order for this to go forward. So let's take a look at this example and let's kind of figure out what they do. Let's take a ring this time just because we haven't used one in a while. And then we've got a double bond with a CH3 that's here. And then I'm going to draw a big long arrow and I'm going to put Hg and then O2CCF3 2 and then CH3OH and then down here NaBH4. Let's talk about what happens. All right, so just like before, I'll do my starting product or my reagent. There we go. I know that my double bond's going to break, so I'll erase it. 2 sites of attachment open up, one there and one there. Now let's take a look at these carbons. This carbon to the left, there's 1, 2, 3, 4 bonds, so there's no hydrogens here. And this carbon to the right, there's 1, 2, and 3, so there's 1 hydrogen here. So when my mercury goes on, it's going to go on to that spot because that's normally where the hydrogen would have went. Well, in doing so, we have a carbocation that has now slightly formed or will form, but a group needs to come in and take the spot all at one time. And this new group, it was HOH in our other examples, so OH was added on, but here it's O and whatever else comes with the alcohol. So OCH3. And then finally in step 2, the sodium borohydride comes in. So it takes the mercury and it erases it. And it says, mercury, you got to go. I'm tired of you. And a hydrogen gets added on there instead. Well, we don't have to write the hydrogens. We can completely erase that if we want. And there is a cleaner form of the product that we have formed. Notice here, this forms ethers. Same kind of similar story that we've seen before in the past, right? We talked about alkenes reacting with acid and water to give us alcohol. And then we talked about alkenes reacting with acid and alcohol to give us ethers. And folks, this is just another way. So just like before with water in the oxymercuration version, we add OHs on to get alcohols. And as in this case, we add OR groups on to get ethers. It just is another way to form an ether versus the alcohol and the acid addition that we learned later on in a previous video. The difference, no rearrangement happens. That's the kicker. So alkoxies are great if you want more control over where these groups are going to go. If you don't really care, then use the acid alcohol version or the acid water versions. They'll give you kind of similar things. So that's where this video is going to stop. I know, I've babbled on too much about oxymercurations. I know you're not excited about these, right? I mean, nobody really is. I mean, it just looks like it's getting more and more complicated as we go. Like, how on earth does he expect me to memorize all of this stuff? I don't want you to memorize. I want you to learn them. I want you to learn the procedures. That's what this is all about. And notice the procedures have all been the same. Double bond breaks, 2 sites of attachment open up. We have one thing that adds on to the side with the most hydrogens, and then we have the other thing that adds on to the other side. The only difference is that we're questioning on whether or not that group will rearrange. It's the same process over and over and over and over and over. We're just using different stuff. That's all that we're doing. So in the next video, I'm going to start with examples. Again, examples are the man's best friend, woman's best friend, right? So this is going to be your best friend as well. So in the next video, that's where we're going to start. And we'll do a couple of these examples and reactions and talk about how to make products and so forth. And then we'll keep trucking on in the world of reactions of alkenes.